Okay guys, so today I'm going to give you a little bit of a review on the Vsepr theory. We do have an exam on this tomorrow. Just to get started really quick, we're going to start with Lewis structures. Remember, this is the beginning of everything. So if you have a molecule such as SO3, we're going to figure out what is the molecular geometry of this structure. Now, in order for us to do this, what we're going to do is count how many valence electrons are going to be displayed in our molecule. We start off with the first element. We have one atom of sulfur, and we're going to multiply it by the valence. Now sulfur has 6 valence electrons for every one atom, and we're going to add it to the second one. Now we have 3 atoms of oxygen, and oxygen happens to be in the same group, so we have 6 valence electrons for every one atom. If we do the math here, we should get a total of 24. So when I draw this molecule, I have to show 24 valence electrons. I'm just going to rewrite it up here so I can help us. Now we're going to put sulfur in the center, since there's less sulfurs than there is oxygens. And we're going to attach it one time to each oxygen. Now remember, there's 3 oxygens, so we have to make sure to attach it to at least 3 oxygens. Okay, from here I'm going to draw the lone dots. Now I just want to see if this structure will work. If it doesn't work, we'll go ahead and see what we can do. Remember that every atom has to have 8, unless you're talking about boron and indium. Here, if we do the count, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. So unfortunately this molecule does not work. Now whenever we have a problem like this, what we're going to do is just go ahead and introduce double bonds. Okay, so I'm going to go ahead and redraw the molecule just like we had it. SSOO. Okay, here we go. Here, let's go ahead and introduce one double bond. It doesn't matter where you put it. You can put it to any oxygen. And I'm just going to do that so it can help us reach our 24 count. Now let's go ahead and count this again. If we need to add more double bonds, we will. But let's go ahead and check this. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So that matches a 24 that we should have had. Okay, so this is going to tell us that this is a structure for SO3. Now, I know on your worksheet some of the things we're asking for resonance, and some of you guys have been asking me, well, what is resonance? What is resonance? Now notice here inside this molecule, this double bond is present here. And you may be wondering, well, why does that double bond there, and how come all the other ones are not treated equally? Well, that's what resonance means, is that double bond is really moving between all the oxygens. So that double bond is not necessarily just there, okay? That double bond switches from that oxygen to this oxygen to this oxygen. So there's 3 really ways to draw this picture, and that's what resonance means. It's like there's just more than one way to draw a molecule, since that double bond is consistently moving. Okay, so that's one of them. The other one could be like this, the double bond in the bottom. And another one could be the double bond on the left side. These are all the resonance structures for this molecule. Now, take note, I did not draw the lone pairs, but this is what that means. It's just look at that double bond that's moving. There's one, there it is on there, and there it is on this molecule. That's all that resonance means. This one happens to have 3 resonance structures, just because that double bond can move in 3 places. So I hope this answers a question regarding resonance. So in order for us to continue with this, we're going to go ahead and draw it, okay, any way that you like. Okay, we're going to start by identifying what is the number of lone pairs that we have on the center atom. Now lone pairs, remember, they have to be, for every one pair we have 2 electrons. Okay, so how many lone pairs do we have present in the sulfur is what we have to ask ourselves. Now, if we notice lone pairs around our sulfur, we have 0. Therefore, we're going to look on 0 in our worksheet where it has lone pairs. Now, number of bonding. Now, the double bond is going to count as one bonding pair because it is just bonding to one thing. So this is one bonding, this is 2 bondings, and this is 3 bondings. So we have 3 bondings. So we have 0 lone pairs and 3 bondings. In order for us to figure out the geometry, we're going to go ahead and access our notes. Now, if we go back, and I'm going to go ahead and exit the screen just so we can look at our notes. We're going to look under 0. Okay. See if I can exit this. Okay. Number of lone pairs on the front one. Notice we're going to look for everything that has 0. So anything that doesn't have 0 we can go ahead and scratch out. So we can scratch out anything that doesn't have 0 on the first column. So that cancels that out, that cancels that out, that cancels that out. Okay, and so we have 0 and we had 3 number of bonding. So if we notice, we're going to look for 3 on the second column. This is the one we find here. Okay, so 0 and 3. So our molecular geometry, is gonna be trigonal, and I'm just gonna go ahead and put trig to make it short, planar. Okay, this is how we're gonna do it for these problems, so we can identify resonance. Now it's very simple. It's very easy to find. This is what you're going to be doing tomorrow on your exam. Now, a real quick note that I want to make. We're going to have some things that are going to violate the octet rule. And that's going to be okay. For example, boron and indium. Sometimes you're going to have 6 valence electrons around them. That means you're going to have B, for example, bonded to 3 things. And it's not going to have the complete octet. That's okay. It happens sometimes. Boron and indium are very good examples of that don't have a full octet. Now there's other molecules such as SF6 and PF5. These are going to have what we call extended octets, which means we're going to have more than 8 electrons around the center atom. And that's okay as well. So remember that all the F's have to be bonded to the center atom. Okay, so don't be scared to mess this up. This is right. This is the correct structure for them. We just have to draw in the lone pairs. Okay, this is what we're going to be doing. It's very simple exam, very straightforward, and so on and so on. We do that the same for PF5. This is okay. Some of these have expanded octets. Whenever you have 3 halogens, remember halogens, group 17 elements. So group 17, these elements, you will never double bond them. However, if you have I3 to the -1, this becomes a violation of the octet rule. Remember that I told you, you can never double bond these groups. Never. However, in this case, there's 3 of them. One of them has to be the center atom. Therefore, it's going to have 2 bonds. So here, if we do the math, it's 7 multiplied by 3, which is going to give us 21 plus 1 valence electron. That's what the minus on I3 to the -1. That little minus means add 1 valence electron. So if it had -3, you would add 3 valence electrons. If it had +1, you subtract 1 electron. So here, in total, we're going to have 22 valence electrons. Here, we're going to have to put one of the i's in the middle. That's just the rule. We're going to go ahead and put the i's. From here, we're going to go ahead and fill in the electrons. Make sure that all of them have 8. And here, okay, we're going to make sure those have 8 too. Now, if we do the math, remember that we should have a total of 22. Let's go ahead and count. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So we're still missing 2 electrons. When halogens bond, if this is the case, never double bond them. Instead, what you're going to do is just add that extra lone pair to the center atom. And that's okay. That happens as well. In this case, we're just going to go ahead and add this pair here. And if we do our math now, we should add up to 22. Now this is very simple, very straightforward. Here, if we were going to go ahead and look at our table, what we're going to see is that we have 3 groups of lone pairs in the center atom. So here we're going to have 3, right? 1, 2, 3 groups. And how many things is it attached to? Well, 1 and 2. So we're looking for 3 and 2 in our table. Now I'm going to go ahead and switch back to the table so it can help us a little bit. Here, we're going to look for 3 and 2. Okay. So if we look for 3 and 2, this is it right here. So our molecular geometry is going to be linear. Okay. Very simple. This is what we'll do tomorrow in our test. If you have any questions, you can go ahead and let me know, and we'll get those addressed.